Okay, so today I'm not going to make a review of the last classes because we're going to do something very different. We're going to start studying particle detectors. I'm going to introduce only the basics of particle detectors, and you can learn more about it in the relativistic quantum information course. Relativistic quantum information protocols and quantum field theory, I think, is the correct name. The RQI course. So here's what we're going to do. We are going to try to understand what is going on in the Unruh effect with a different point of view. Namely, we're going to model a particle detector as a two-level system, so it can go down and it can go up. And we will try to see what exactly happens when I accelerate this two-level system in the Minkowski vacuum. So with it interacting with the Minkowski vacuum, with the quantum field. So this is similar, for example, if you have an electric field and you're going to put an atom interacting with this electric field, and you're going to see how exactly the electron can jump up or down depending on photons that come and interact with it. So this is the basic idea for a particle detector. The way we're going to model it is the following. We start with a Hamiltonian for the detector, which is going to be given by omega over 2 sigma z. So this is an excited state omega over 2 and an unexcited state omega over 2 minus omega over 2. Hence we have Hd on the excited state equals omega over 2 on the excited state, and Hd on the ground state equals to minus omega 2 on the ground state. Now we want to make it interact with the field somehow. So we're going to add an interaction Hamiltonian in the interaction picture given by epsilon times Pauli x of tau, where tau is the proper time of the detector, tensor the field along the word line z of the detector. This word line will take to be in radar coordinates, in Hindler coordinates, which are given by r cos a eta and by t equals r sinh a eta. It is going to be tau for eta, 1 over a for r, and 0 for the remaining components, y and x, y and z. So this is the trajectory. This Pauli matrix is evolving in time because we are in the interaction picture. And at last, we have a Hamiltonian for the field. Now this is a Hamiltonian that generates translations along the inertial time. We want to get a Hamiltonian that generates translations along the proper time of the detector. To do so, we notice that 1 over d tau equals I.
Why is the Pauli matrix a function of tau?
Sorry?
So the sigma x Pauli matrix, why is it a function of tau?
Oh, because we are in the interaction picture, so this evolves.
I see. But the form it so it will what is the evolution like? I mean,
Oh, it is going to be sigma x of tau equals e to the I tau hd sigma
because
x e to the minus I tau hd.
okay. Thanks.
You're welcome. So we have 1 over d tau equals I dt d tau d dt, which then equals dt d tau h phi. Hence, the complete Hamiltonian for the system is going to be given by h phi dt d tau plus hd for the detector plus the interaction h int. Okay, so far so good. I'm going to assume so.
Sorry, could you explain what was H5? Like H5 was the Hamiltonian corresponding to the field
To the
operator.
field. So it's whatever Hamiltonian the field has, which is the Hamiltonian for the Klein-Gordon equation. We won't use it explicitly.
Okay, so it's just a total time derivative with respect to the original xt coordinate.
Yes. Is the AI ddt for the field. Hence, we get to this. And we want to do something with this, namely, we're interested in computing what is excitation probability. So if I have a state, I have the ground state, G, or down arrow, let me use down arrow, and the field is in the vacuum. I want to know what is the probability that it goes to the up state with the field in some other state. Okay, so I want to compute the amplitude, which is lower to upward of phi given by this, where this is the evolution operator in their interaction picture. To write this, we're going to use a Dyson series. So we have that this operator is 1 plus a sum from n equals 1 to infinity of, let me remind myself. Yes, it is. Sorry. The time order.
Sorry, could you motivate why did you choose the form of H interaction to be that particular choice?
Of the
Like, what was the
interaction,
motivation for it?
because this has roughly the form phi with an epsilon in the front. So what you get is this thing that interaction with the field can flip the state.
Right. So, and if I'm clear here, so there are two Hilbert spaces we are talking about. One is a two-level system, and then the Hilbert space of the Fock space, maybe for the quantum field.
Yes.
So the phi operators will act on that particular quantum field, right? Quantum field state.
Yes.
So are we always taking it to be in the vacuum, or what state are we choosing for the ultimate, like the evolved state?
We are assuming the initial states to be vacuum.
Right.
So
I was asking, like, after evolution, after applying the UNT, what state do you expect it to be, like the phi state that you are writing?
Oh,
The
it
up
doesn't
arrow
really
with the
matter.
phi.
It
Oh,
doesn't
okay,
really
okay,
matter.
okay.
It will come out of the expression.
Okay, so it's not the usual Fock space state.
Yeah, it can be a Fock space state. It could be, for example, a different state on the Fock space, but
Okay,
it is not necessary to specify it.
I see. Okay.
But it's a vacuum of the free Hamiltonian, right?
Yes. Yes, it's for the free Hamiltonian. So we're going to have here X. Keep clicking here. Tau prime tau plus this goes to minus I tau prime. That yes. H int tau 1 d tau. And to first order in perturbation theory, we're going to have 1 minus I epsilon tau to tau prime psi x tau 1 times phi of z tau 1 d tau 1. Hence, the amplitude we want to compute, which is down to up at phi, it is going to be E phi G0, which vanishes because E and G are orthogonal, minus I epsilon tau prime E psi x Q1 G phi. Oh yes, there's no need for a time order in here because we are with a single time insertion. E of tau 1 0 d tau 1. Now, hence, this becomes simply e to the minus epsilon tau prime E 6x T1 G phi of C tau 1 0 d tau 1. Now we compute what is this expression in here. E psi x tau 1 G, which equals E to the I tau HD psi t e to the minus I tau HD. There could be also the Hamiltonian for the field in here, but it would just cancel because it commutes with sigma x G, which becomes E to the I tau omega 2 by applying it to the E state, sigma x E I tau omega 2 by applying to the G state, and hence we get to E I tau omega E sigma x g. Now, we know that E can be represented as 1, 0, G can be represented as 0, 1, and hence E sigma x G equals 1, 0, 0, 1, 1, 0, 0, 1, which is going to give us 1, 0, 0, 1, 1, 1, 0, 0, 1. Therefore, this amplitude can be written as minus I epsilon integral from tau to tau prime e to the I tau 1 omega phi phi z of tau 1 0 beta 1. Okay? So we get to this. Now, what we actually want to compute is the probability for excitation of the state. This is given by the integral of a lower to upward of phi squared integrated over all phi. Hence, using this formula, we know that to first order in perturbation theory, what we are going to get is minus epsilon squared. Is correct? Oops. Yes, epsilon squared integral from tau to tau prime. There are actually two integrals from tau to tau prime. To the I tau 1 omega e to the minus I tau 2 omega 0 phi, just this means phi of tau 1 phi 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 of tau 2 0 d tau 1 d tau 2 d phi. Since we have a d phi and we have here this cat phi bra phi, we know that we can just write this as a resolution of the identity, and we get from tau to tau prime, from tau to tau prime, e to the minus I tau 1 minus tau 2 omega, and a 2-point function z tau 1 z tau 2 at a vacuum d tau 1 d tau 2. All right. Now we can rewrite this by a change of variables as e2 from tau to tau prime, and the second integral let me find it here. Oh, sorry, yes. Before anything else, for the trajectory we picked, we have the 0 by zeta 1 by zeta 2, 0 equals actually, and this can be seen from the usual formula for the 2-point function that you can find in Bogoliubov and Shirkov, for example, with a little manipulation that is available in the lecture notes. One gets that this is equal to the distributional limit, perhaps I'm going to 0, of minus a squared over 16 pi squared sinh squared of a over 2 tau 1 minus tau 2 minus I epsilon. So that seems to be it. Yes, it is. Therefore, the probability we are computing between times tau and tau prime equals minus a squared epsilon squared over 16 pi squared integral tau to tau prime integral tau to tau prime of e to the minus I omega tau 1 minus tau 2 over sinh squared a over 2 tau 1 minus tau 2 minus I epsilon d tau 1 d tau 2. We can make a change of variables so as to write from tau to tau prime
What happens to the W limit?
the W limit is still there, but now I'm just considering it as the... Yeah, I should actually write it. Sorry. It now becomes a regular limit outside of the integral.
Sorry, could you recall what the W limit was?
It is a distributional limit. It means you first integrate it around against something, and then you take the limit.
Okay.
So now we integrated it against something, and now I'm taking the limit.
Okay.
So this is similar to the usual plus epsilon convention, plus I epsilon convention in quantum field theory. So it's just to dislocate the poles a little bit. Okay? And we have here is actually now an H. A tau minus tau 1 over 2 A tau prime minus tau 1 over 2 e to the minus I theta. Let me just come up with a variable here. Psi, which is the difference between tau 1 and tau 2, divided by sinh squared A over 2 psi minus I eta. D psi d tau 1. Now, instead of computing this, it is easier for us to compute the rate of transitions between from the lower state to the upper state. This is given by the probability, by the limit actually, of tau prime goes to infinity and tau goes to minus infinity, of the probability down to up of tau prime tau over tau minus tau prime minus tau. This gives us, from the previous equation, this is going to be given, excuse me, let me actually change my notation a little bit so the epsilon is clear. This becomes simply a
Your
square.
definition of psi was tau 1 minus tau 2, right?
Sorry?
What was
Yeah,
the definition of psi?
tau 1 minus tau 2.
So why did the limits get a factor of a?
Let me check.
Also, I
Yeah,
think there
sorry.
would be an overall minus sign, which cancels out.
Sorry, it is actually a times tau 1 minus tau 2, a over 2 times tau 1 minus tau 2.
Right. So,
Nice catch.
and then the front also there will be some changes. It will be a only now.
Minus 2i
With the plus sign.
minus 2i omega psi over a, and this a here does not have a square anymore. Okay.
Sign should also change, right? It should be a plus, I think.
I don't think so.
Okay, so you're changing tau 2, right? So it's tau 1 minus tau 2 is now psi. So d psi should be minus. Okay. I think it should be that. Yeah.
Okay.
Yeah, okay. Yes, that's okay.
All right. So now we have here minus a epsilon 2 over 8 pi 2. One of the integrals is going to be cut off with this denominator. The other one simply becomes minus infinity to plus infinity, e to the minus 2i omega psi over a. divided by sinh squared psi minus I over E minus I epsilon d psi. Now this integral, this is a Fourier transform. It can be computed with the residue theorem. And at the end of the day, we get that the rate of transition, the rate of excitation, is given by epsilon 2 omega over 2 pi e to the 2 pi omega over A minus 1. Similarly, we could have computed the rate from up to down, and that would be just changing plus omega to negative omega, and it would give us epsilon squared omega over 2 pi 1 minus epsilon 2 pi omega A. There's a minus in here. This implies that R from the ground to the up over R to the up to down equals to E minus 2 pi omega over A. This is called the tail balance. Which is the, let me see which is a hallmark of a system in thermal equilibrium. So it gives us a thermal equilibrium at beta equals 2 pi over A, or T equals A over 2 pi. So this is another way to get to the Unruh effect. And this time, I like this demonstration because it is particularly physical and experimental, so to say, because you are actually picking a particle detector and accelerating it and seeing that you actually are measuring particles with a temperature, with a thermal equilibrium. So this is much less abstract than the other derivations we have done. And well, I think that's it that I have for today. It's a quite short lecture, but it is an introduction to particle detectors. You're going to see more of this if you subscribe to the relativistic quantum information course. In particular, more complicated particle detectors and probably more uses for them than only finding the Unruh effect. But they are a very interesting tool to probe many effects when you have less symmetry, for example. Although the calculations get difficult, fairly easy. Any questions?
I should have asked this earlier, David, but what was capital omega?
What was capital?
The capital omega that you're writing. That's the angular momentum? Or
Oh no, capital omega is an energy scale. So it is the difference in
or
energy between the up and the lower states.
okay.
Here it is.
Okay.
So the up state has omega over 2, the lower state has minus omega over 2.
And the R down to up is the rate of change of probabilities, is it?
Yeah, it's the rate of excitation. So it's probability per time.
Can we run into some trouble by the order of the limits here? Like, I mean, it's an integrated quantity we are dealing with here, right?
Yeah, I admit
In the
this
definition of R.
Yeah, I admit this step is a little bit physicsy, so to speak, but as far as I know, there's no issue with the limits.
Okay. So the rate of change, sorry, could you repeat what was R? Like the probability change per unit, how to define R?
Yeah, R is essentially probability per time, so how often you're going to see a particle appearing in your detector. Any other questions?
Just I have one question, maybe naive. So here we are considering a point-like detector, right?
Sorry?
Am I audible? We are considering over here a point-like detector,
Yes.
and you said initially that at point like our whole state is not well defined. Like we need to do some sort of smearing or some sort of that. We, and like we defined smeared field because we had problem with normalization or something like that. But here we are doing with point like detectors.
Yes,
So
we are dealing with point-like detectors. They do have some problems, and you can get rid of some of the problems by smearing them. But that is a topic for the
we are
RQI course.
we are not getting any divergence over here. While in normalization, we get divergence with only this kind of field.
Sorry, I did not understand.
I'm saying that we are not getting any divergence in transition rate with this without smearing field. Our rate is well defined, right?
Oh, R is well defined.
Yeah, R is well defined, but you said that phi is not well defined. We have to smear phi.
Oh, okay, yes, in principle, we have to smear phi. So in order to have a completely well-defined phi. But I'm doing this in the way we usually do quantum field theory in flat space-time, in which we treat the things as being point-like. That is not exactly the most mathematically correct way, so it is a bit physicsy in the sense that I'm not taking it to a mathematically rigorous approach.
Mhm.
For a mathematically rigorous approach, we have, for example, the algebraic approach.
Could you provide some reference where this thing has been done rigorously?
Um, I have a guess of a paper that might do this a bit more rigorously. Not exactly this calculation, but it works with particle detectors in a more rigorous way, which is, let me find it here. The name. Here. Try. This paper. It was written by my advisor. I think it is a little bit more rigorous to dealing with particle detectors than I'm being here.
Okay, thanks.
So it might be a little better. I'm not completely sure whether it is sufficient to answer a question, but I think it might. Any other questions?
Thanks, got it.
You're welcome. Okay, so I think we'll stop here. Let me stop the recording.